mid here on this lecture. Between the previous lecture and this one, there should be a big gap, and the gap, as you know, is due to the ESE and some examination, both PG and UG last semester. We are engaged with those examination, assignment vivas and MCQ quiz and etc. And due to that, unable to post a new lecture in the continuity, and therefore let me brief you about the previous lecture so that the link can be established and we can have a fair discussion on this lecture as well. Well, have been discussing metal ligand bonding. In metal ligand bonding, we discuss different theories to establish how metal and ligand have different type of interaction, in which we have discussed little bit about crystal field theory, VB approach, uh, and then now we need to discuss the molecular orbital theory, or we can say ligand field theory, so that it clarify the limitation which we have gone through for crystal field theory and in VB approach or VSCPR theory. So to remove that limitations, we studied three different geometry in metal ligand interactions. First is octahedral geometry, second is tetrahedral geometry, third is square planar geometry. In octahedral geometry, we studied three different type of interaction. One is sigma interaction between metal and ligand. The other one is sigma donation, pi donation interaction, and the third one is sigma donation, pi donation, and pi acceptance interaction between metal and ligand. Then after we discussed tetrahedral geometry. In tetrahedral geometry, we have two interactions only. One is a sigma donation uh, between the metal and ligand, and the other one is sigma donation and pi donation interaction. Tetrahedral geometry should not have pi acceptance interaction. So there is the limitation in the tetrahedral geometry. And the third geometry we have studied, that is square planar geometry. In square planar geometry, all these interactions are possible, because when you compare the square planar geometry with octahedral geometry, you found that the axial ligand which is oriented on z axis, ligand 5 and 6 are missing. So we have 1, 2, 3, 4 in a planar arrangement, that is a square planar geometry. So that is the difference between the octahedral geometry and square planar geometry as far as geometrical differences is concerned. But in square planar geometry, we studied sigma donation interaction, sigma donation and pi donation interaction, and sigma donation, pi donation, and pi acceptance interaction. So these are the three different geometries and different metal ligand interactions we have studied there. Well, the temptation of learning this metal ligand interaction, then after I have clarified by putting some notes of the limitation of CFT, how we can rule out the limitation of CFT, and what different information can be obtained. See, if you have information of symmetry and this improved ligand field theory, or we can say molecular orbital theory of a complex compound, you can easily study the spectroscopy. So these are the base of learning the spectroscopy. That is the temptation behind learning these theories. Once you learn these theories in the uh, more semesters, when you study spectroscopy, it would be easy little bit to understand the spectroscopy, the pi to pi star, sigma to pi star, sigma to sigma star interactions in the spectroscopy. This can be easily you can learn by having this basic information of metal orbital theories. So three different geometries we have studied, and now we need to discuss the effect of pi bonding on the value of delta O, that is a splitting energy. So why there is a limitation in CFT? We just learn what are the limitations, but why those limitations are there and how we clarify those limitations can be explored by these theories. So these are the common theory of all the three different geometrical shape you have studied for complex compound. So today we will going to discuss this effect of pi bonding on the value of delta O, that is splitting energy, by considering the example of octahedral geometry, and that can be implemented to tetrahedral geometry up to some extent, and it can be implemented to square planar geometry completely. So this is the effect of pi bonding of delta O, that is a splitting energy in the complex compound. I am Dr. Devang Pandya from the Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well, let's start the effect of pi bonding on the value of delta O, that is the splitting energy. In order to discuss the effect of pi bonding on the value of delta O, we shall consider two types of molecular energy level diagrams of octahedral complex. Here, when I say two type of diagrams, energy diagrams for octahedral complexes, molecular energy level diagram, that is MOED, we have used the term MOED for that. Two type means ones in which we have focus for sigma interaction only, and the other sigma and pi interaction. Now sigma and pi interaction, there are two kind of pi interaction that you need to keep in mind. One is pi donation interaction and the other one is pi acceptance interaction. So basically there are three different parts, but here we will classify the MOED for only two considerations. One is sigma interaction, the other is pi interaction. In pi interaction, there is some two part, that is pi donation interaction and pi acceptance interaction, that you are much familiar now with that. So these two diagrams we will going to see in the next slide as figure 1 and 2, and we're going to discuss what is there in the only sigma interaction for the value of delta O and how it get changed when there is two type of pi interaction taken place between metal and ligand. So that is the discussion of today's lecture that we need to take into account. I am going to show you the figure 1, and the figure 1 has certain limitation. The limitation is that this figure is not a complete MO. It only shows the energy level diagram showing the effect of pi bonding on the MOED of a metal complex, and hence the non-bonding ligand or pi orbital of T1G, T1U and T2U symmetry have not been shown over here. You can see here, this is the splitting energy. This is T2G non-bonding in a sigma interaction. So this is a energy gap between sigma T2G non-bonding as well as EG sigma star ABMOs, and that difference is known as delta O. And the energy gap between T2G star pi ABMO and sigma star EG star sigma ABMOs, that energy gap is mentioned here by delta dash O. And you can see here this splitting between delta O and delta dash O. Delta O is greater than delta dash O. So that the things that you need to keep in mind for this figure 1. And these are the ligand group orbitals, LGO, sigma as well as pi, and this is the metal orbital in metal ion d orbitals. So sigma and pi orbital of LGO and metal have interaction, and the splitting will taken place in this form. And what effect of this pi interaction is there, what is the effect of sigma interaction is there on the splitting energy, that is the point of discussion today for this figure 1. How figure 1 differ with figure 2, that we're going to discuss as well. This is figure 2, and figure 2 also indicate the effect of the pi bonding on the MOED of a complex, and here also the non-bonding pi orbital of T1G, T1U and T2U symmetry have not been shown. Here you can see the splitting energy is like this one. This is T2G metal ion orbitals, and energy gap is between T2G metal orbitals and EG star sigma ABMOs, that is indicated by delta O. And this one is pi bonding BMO with sigma star ABMO, and that energy gap is indicated by delta dash O. So in figure 2, delta SO is greater than delta O, and that is how the difference is there in the splitting value of energy when the pi interaction we introduce in the metal ligand interaction. And that is what missing in CFT, crystal field theory. Crystal field theory is unable to explain the difference in the splitting of d orbital of central metal ion if the ligand change into spectrochemical series. And here we are able to explain the difference uh, by indicating this different type of interaction: sigma interaction and pi interaction, sigma interaction, pi donation interaction, and pi acceptance interactions. So that is what the difference is there in these two figures, and that we're going to elaborate these two figures as well in this later presentation. Well, in this both diagrams, what we need to point out, 3 points would be there. The first point indicate that we have depicted the formation of two Eg sigma BMOs and two Eg star sigma ABMOs, 3 T2G pi BMOs and 3 T2G star pi ABMO. So here there is the interaction of sigma donation and pi donation, and this kind of molecular orbitals are involved in this splitting, and that will going to give you the idea of either the better splitting or less splitting in the complex compound. In the second point, we need to focus on the two degenerate Eg sigma BMOs and two degenerate Eg star sigma ABMOs are generated by overlap between two ligand sigma orbital of Eg symmetry with metal orbital of the same Eg symmetry, and the Eg symmetry is dz square and dx square minus y square of the metal ion d orbital. So this interaction is a sigma donation interaction. Clearly it mentioned that sigma BMOs and sigma star ABMOs, they are generated by the overlapping of two ligand sigma orbital of Eg symmetry with metal ion having the same Eg symmetry, that is the z square and the x square minus y square. Now Eg sigma BMOs have lower energy. Always you know that BMOs have lower energy compared to ABMOs. So that is there in the second point. This type of overlap between the orbitals is called sigma overlap, and that interaction is known as sigma interaction, and in short we are branding it as sigma donation interaction only. It should be noted that 3D orbital of T2G symmetry, which include 3D XY, 3D YZ and 3D ZX orbitals, do not participate in sigma overlap, and hence these orbitals remain non-bonding molecular orbital, and therefore their energy will not get changed, and the energy is quite equal with the 3D orbital of free metal ion. So the energy of T2G symmetry in MO diagram remains similar with the 3D orbital of free metal ion, and therefore it considered as NBMO, non-bonding molecular orbital. And the third point, the 3 degenerate T2G pi BMOs and 3 degenerate T2G star pi ABMOs are produced by the overlap between 3 ligand pi orbital of T2G symmetry and the metal ion T2G orbital, that is the XY, YZ and ZX. Always we know that the planar orbital, when there is actual interaction in octahedral geometry or either in a square planar geometry, axial orbital result into sigma interaction. This planar orbital and participate into pi interaction. So there should be a pi interaction between T2G symmetry of the metal ion with T2G symmetry of the ligand, and that overlap result into these 3 degenerate pi BMOs and 3 degenerate pi star ABMOs. Now these T2G pi BMOs have lower energy. Always we know that the BMOs have lower energy compared to ABMOs. So that is there. The overlap between orbitals leading to the formation of T2G pi BMOs and T2G star pi ABMOs is called pi overlap or pi interaction. Now this pi interaction is of two kind, as already we have studied in our previous lectures. One is sigma donation interaction where the ligand acts as pi base, and the other one is the pi acceptance interaction where the pi orbital of ligand act as pi acidic ligands, that we will going to see in the later presentation. In this pi interaction, three ligand pi orbital may be filled orbitals. When there is filled orbitals, the example would be mostly halogens, fluoride, chloride, bromide, iodide, or other certain element or ions which have filled pi orbitals. Or in certain other case, the pi interaction will result if the ligand have empty pi orbitals. When empty pi orbitals are there, the example is always would be cyanide, carbon monoxide, nitrosyl oxide, triphenyl phosphine, alkyl phosphine, hydride ions, etc. So these two type of interactions is there as far as pi interaction is concerned. Uh, One is through filled orbitals and the other one is through empty orbital. Filled orbitals always result into pi base and empty orbital always result into pi acidic orbitals, that we're going to see later. If the ligand pi orbitals are filled and the metal d orbitals are empty, then pi interaction is represented as ligand to metal pi interaction, in which the filled ligand orbitals, pi orbitals, act as donors and they can be branded as Lewis base. In MCQ, these are the terms which will be more useful, so you need to pay attention here, students. And similarly, when we discuss the ligand pi orbitals which are empty and the metal d orbital which are filled, then whatever pi interaction is taken place is represented as metal to ligand pi interaction, in which empty ligand pi orbital act as acceptor and they are branded as Lewis acid. So that you need to keep into mind. And the fourth point, the delta O, that is of splitting energy, represents the energy gap between Eg star sigma ABMOs and non-bonding metal ion orbital T2G symmetry, that is 3dxy, yz and zx, when only metal ligand sigma bonding is considered. So this energy gap represent only sigma donation interaction, and that energy gap is between Eg star sigma ABMOs and non-bonding molecular orbital, that is NBMO T2G symmetry of the central metal ion, that is 3dxy, yz and zx. So that represents the splitting energy delta O in a sigma bonding interaction. Now let's recall the figure 1 once again. This is our figure 1, and in this figure 1, the ligand pi orbital used for the formation of 3 T2G pi BMO, that is there in the blue circle, 3 T2G pi BMO and 3 T2G star pi ABMOs, that is in the blue circle over here as well, and these are filled. And when it is filled, the example will be fluoride, bromide, chloride, iodide, etc. and have lower energy than the metal T2G orbitals. So this has lower energy than the metal T2G non-bonding orbitals. Hence, delta dash O is the energy gap between Eg star sigma ABMOs and pi star T2G star pi ABMOs. When both sigma and pi bonding are considered, sigma donation and pi donation considered, our energy gap is only this much. sigma donation, pi donation. Only sigma donation, energy gap is this much. That is represented by delta O. Delta dash O, that is sigma donation as well as pi donation. So that way the MO diagram is shown over here. This is not a complete MO. This is overlapping MO of sigma as well as pi donation, sigma donation and pi donation interaction, so that we can understand what is the effect of pi on splitting. It may be noted that the value of delta dash O decrease relatively to the value of delta O where metal ligand pi bonding is absent. Non-pi bonding case, delta O is higher. Delta dash O will get decrease. In other words, pi bonding leads to decrease in the value of delta O. When pi bonding take place, delta O, which is this much bigger energy gap, reduced to delta dash O. That means the value of delta dash O is less than that of the pairing energy. Dash O is less than that of the pairing energy. And as a result, what happened when pairing energy reduced? We're going to get the high spin complex. The ligands such as fluoride, chloride, bromide, iodide or other ligand which have filled pi orbital, which contain a filled p pi orbital, exert weak ligand field. They are not able to split d orbital more effectively and hence generally form high spin complex. So when the pairing energy is greater than that of the splitting energy, you will always get high spin complex. This interaction is found in oxide and fluoride complexes with filled low energy 2p orbitals. Filled energy, then we'll get this kind of things and you will get high spin complex. These ligands can act as pi donors from filled ligand orbital to vacant or partially filled metal pi orbitals. The oxide and fluoride have all their 2p orbital that is filled. When we talk about oxygen, the electronic configuration is 2s2 2p4, and when we discuss regarding oxide 2 minus ion, then its electronic configuration is 2s2 2p6. Similarly, when we discuss about fluoride as an atom, the electronic configuration is 2s2 2p5, but F minus, that is fluoride ion, then the outermost orbital would be 2s2 2p6, and in both the case of oxide and fluoride you can see completely filled p pi orbital would be there, and as a result its delta dash O, that is splitting energy, is always lower than that of pairing energy. Hence this complex of oxide and fluoride is always high spin complex, and the splitting energy is always lower than that of the sigma donation interaction. One such filled orbital is used in sigma bonding with the metal ion, while the other two filled orbitals are used in pi bonding. Okay, so out of this, some of used for sigma bonding, while metal ion with the metal ion, sorry, and the other two filled orbitals used for the pi bonding. Out of this type of interaction is found in magnesium hexachloride 4 minus ion complex. This is octahedral geometry, and the chloride ion act as sigma donation pi donation, and it result into a high spin complex. Well, let's discuss the figure 2. On the other hand, we have in figure 2 the ligand pi orbital used for the formation of 3 T2G pi BMOs and 3 T2G star pi ABMOs are vacant, that is empty. Ag pi star ABMOs in the cyanide ion case, either carbon monoxide, nitrosyl oxide, or trialkyl phosphine, triphenyl phosphine. This type of ligand which have this antibonding pi ABMO which is vacant and have higher energy than metal T2G orbitals. So the delta dash O, that is the energy gap between Eg star sigma ABMOs and T2G pi BMOs, when both sigma and pi bonding are considered, is going to be more compared to sigma delta O, only splitting when uh, uh, only sigma interaction is there. It may be seen that the value of delta dash O increases relatively to the value of only delta O. That is, when I say only delta O, that is only sigma donation interaction between metal and ligand. When I say delta dash O, that is pi interaction between metal and ligand. So in pi donation, we studied that dash O is less compared to delta O. Now in pi acceptance, delta dash O increases relatively to the value of delta O. Where metal ligand pi bonding is absent, non-pi bonding case is there. In other words, pi bonding leads to an increase in the value of delta O. That can be seen over here. You can see that delta dash O is greater compared to this. So this is only sigma donation interaction, and here pi acceptance interaction. So this delta dash O is greater than that of delta O. As a result, what happens? As a result, the value of delta dash O is more than the value of pairing energy. So delta O is higher than that of pairing energy. So energy gap is high when ligand approach to central metal ion, splitting get increase, and as a result, we're going to get low spin complex. The ligand like cyanide, carbon monoxide, NO, trialkyl phosphine, triphenyl phosphine hydride, this kind of ligands contains vacant p pi orbital, exert strong ligand field generally from low spin complexes in which delta dash O is greater than that of pairing energy, which we can found in this MO diagram, which this information can be obtained in MO diagram, which is missing in CFT. So we have explored the limitation of CFT by representing the effect of pi bonding on the value of splitting energy. It cannot be clarified into CFT. It indicates the splitting but cannot explain why the splitting is indifferent into different complex compound when the ligand get changed with the same metal ion. D orbital splitting get different, that cannot be explored in CFT, can be rectified into this MO diagram. This type of pi interaction is found in the complex of phosphine, arsines, etc. Such ligand can act as pi acceptors from metal orbitals to vacant ligand pi orbitals. Pi acidic as well, we can say pi acidic. Now let's compare the value of delta dash O for halide ions used for filled pi ligands. So after learning the impact of pi bonding on splitting orbital, how high spin low spin complex is formed, uh, we can put even the one more diagram which can indicate or the difference between only sigma interaction, sigma donation pi donation interaction, and sigma donation pi acceptance interaction as well, that we're going to put somewhere else, or we're going to have it in a live chat as well. So here we're going to discuss the comparison between the value of delta dash O for halide ions. We have different series in the halide group, fluorine, chlorine, bromine, iodine. So in this four, what should be the order of the value of delta O splitting in this filled pi orbital? The MO energy level diagram, that is MOED, in which halide ions are there. What are the halide ions? Fluoride, chloride, bromide, and iodide, which are used as filled pi ligands, that we can see in the figure 3 in the next slide. This figure shows that the value of for F minus, that is fluoride, to compare the value of delta dash O for halide ions used as filled pi orbital, which we are going to see what are the difference in the value of delta dash O, well, from we can say fluoride to iodide. Here the things is missing a little bit, fluoride to iodide, and we're going to compare the value of delta dash O for this halide in this field orbital. The figure shows that the value of delta dash O, that is splitting energy for fluoride, chloride, bromide and iodide ligands, decreases in this order. Fluoride is having more, we can say delta dash O value, then the chloride is having little less delta O, that is a splitting of d orbital done by fluoride more effectively, which is done by less effectively by chlorine, which is even done by less effectively by bromide. And because the size of iodide is more, it has very less. So because the energy of this pi orbital of the halide ligand increases as uh, we can say the order would be fluoride to chloride, energy of pi orbital of halide ligand increases, uh, chloride to bromide, bromide to iodide. The decreased order of the value of delta dash O explain the decreasing order of ligand field strength of these halide ligands. Now, why halides have different splitting energy with the same metal ion, we cannot explore into CFT. We can explore it here using the MOED diagram. A low value of delta dash O correspond to weak ligand field strength, and that is how study of this will going to give us the spectrochemical series, why one ligand is more effective to split d orbital, why the other ligand is less effective to split d orbital. That can be explored using this MOED diagram and the study of this splitting energy. Where here you can see that T2G to EG star ABMO, that is the delta O in a sigma interaction. But as far as this pi interaction is concerned, you can see that fluoride have little higher delta dash O, but not that much of similar to this. You can see fluoride, iodide is there, very less splitting, weak splitting, high spin, most high spin complex. Bromide is even better, having more delta dash O value. Chloride is even more delta dash O value, and fluoride you can see is quite similar, but not that much as sigma interaction. This is sigma interaction, and this is a comparison between sigma interaction and pi interaction. You can clearly see the pi bonding effect on the splitting energy value or energy gap in the complex compound cannot be explored in CFT, can be explored here in uh, MOD, molecular orbital energy level diagram. So that is how this can be explored in this different ligand, and you can give the ordering of the splitting energy gap here in halogen series. Now, relation between pi bonding ability of ligands and their position in spectrochemical series. So this will going to give us the positioning of spectrochemical series. Now, positioning in spectrochemical series cannot be explored by CFT, can be explored by MOED diagram, MO theory. So that is also how we can clarify the limitation of CFT. We have shown that the ligands like fluoride, chloride, bromide, iodide, etc. Donate electrons present in their p pi orbital to the empty metal d orbitals and form strong ligand to metal pi bond. Such ligands are called pi donor ligand and cause small splitting of d orbital compared to sigma interaction, small splitting of d orbital. These ligands occupy position at the lower energy side of the spectrochemical series. So in spectrochemical series, they will occupy low side. On the other hand, the ligand like cyanide, carbon monoxide, triphenyl phosphine, etc. accept electron from the filled metal orbital in the vacant anti-bonding orbital of the ligand and form strong metal to ligand pi bond. Such ligands are called pi acceptor ligand and cause large splitting of d orbitals. These ligands occupy position at higher energy side of the spectrochemical series, and we have high end, low end. Now you can understand what should be on in the moderate place. Moderate place is sigma donation interaction. Low space in a spectrochemical series occupied by sigma donation and pi donation ligand, and high place in the spectrochemical series, you can now understand, is occupied by cyanide, carbon monoxide, triphenyl phosphine. So this ordering of spectrochemical series can be explained by MO approach, or improved ligand field theory cannot be explored by CFT. Now, relation between pi bonding ability of ligands and their position in spectrochemical series, in which we now going to put some uh, data, some values which clearly mention the positioning of ligand into spectrochemical series. Uh, Jorgensen in 1962, Jorgensen has calculated the value of field factor, that is F, value F, for each of the ligand given in the spectrochemical series. We're going to show it over here. For calculating this value of F for H2 is considered as an ideal ligand, and its value has been taken as 1.00. So now it is a relative value. Water ligand, that is 1.00. Now other ligand, if they are having more value than 1.0, they can be placed in higher energy order, and if it has less than 1.0, it will be placed the lower than the water molecule in the splitting spectrochemical series. So let's see the values of this F, that is field factor value. This is ligand uh, iodine, bromine, thiocyanide, chlorine, nitride, fluoride, hydroxide, carbonate, acid, or we can say acetate ion, etc. And the F value for iodine, it is 0.70, low splitting. Bromine has 0.72, little higher splitting in the delta O value. Thiocyanide, that is 0.73, chloride 0.78. You can see the value get increase of the F value. The splitting energy is higher, and in that order the ligand has been placed into spectrochemical series. Similarly, ligand which have a higher value than water, water is having F value, that is 1.0. uh, this ligand is having 1.02, nitrile carbon, that is 1.15, pyridine 1.23, amine 1.25, and so as you can see, cyanide 1.70, carbon monoxide is quite equal, 1.70, and they are high end uh, ligands in the spectrochemical series. So it may be seen that the value F value increases from 0.70 to 1.70. The power of the ligand to split the orbital also increases. Thank you for paying attention to this lecture. And because I would like to present this lecture on Teachers Day, I am little late. Uh, that is it. Teachers are not common people, and common people are not teachers. Please don't choose to become a teacher until you are worth it. This is the wording of the lady over here. She is a president of Germany, and teachers in Germany have the highest salary in the country, and when judges, doctors, engineers asked the Chancellor of Germany, Angela Merkel, for the same salary, she told them, "How can I compare you to those who taught you?" So let's keep the dignity of teacher. Recall your favorite teacher. Call them today, or either you can say hi, or in a month or a year. Please remember them. They are too much pleased to you. Thank you very much. This is the things which we have discussed today, that is a common for the theory. We're going to learn more in upcoming lectures. Till then, goodbye from my side.